All right, so we've seen how to, like, the theory behind all of the neural network stuff and the convolutional neural network as well, mainly actually on that, but we haven't really seen how to implement it or how to put it into practice with real code. Well, we did, but for, I think it was like stochastic gradient descent, but this is going to be more code from now on. So, all right, so there's a skeleton. So that's the link you want to go to if you want to just follow along, type it through as we're like kind of going over the code and seeing what happens. Like you could run it interactively, or you could just kind of listen to us and kind of see what it does and make comments for yourself. I'd suggest both, but whatever you guys want. And for the slides, there's the link in the feedback form. Don't worry about that part for now. We'll just go in. All right, so today's content would be introduction to PyTorch. Specifically, what I'm going to cover is probably going to be tensors for my part. But other than that, we're going to be trying to see how we load data for our training and testing data sets, how we're going to build the model, like how we're going to just kind of initialize it and then train it, and of course, test it to see how well it's doing. So, all right, before we do anything, does anyone have any troubles with setting up anything? Because I feel like that's probably an issue, but if you want, okay, so like all the documentation we went over from the previous slides in past weeks were to do it on your own system. So this will be on your Google Colab, which means like anyone can type in stuff and run it. But if you do want to do it on your own system, now's the time to ask if you encountered any difficulties. If not, just like give a thumbs up and we'll move on. I'm just asking because we covered it and it was at the end of all our slides. All right, so Gary S, you good? All right.
Yeah.
I guess we're good. All right. So, well, okay. So before we move on, here are the list of import statements. So if you're new to Python or just like do not know what libraries are, so libraries just kind of abstract things that we don't want to implement by ourselves because it would take us forever to do so. And they're streamlined to do what they're best at doing. So we're gonna use PyTorch. So that's import torch. And we're gonna be using NumPy. So these are all libraries that will be useful for computation or building our model or testing or training. So I'll give you maybe like a minute to just kind of copy this part if you have not done already. So this would go in your top part of your skeleton, like before anything else, if it's not done for you already. All right, so guess we could move on. All right, so torch tensors. So what are they? So tensors can be thought of like an array of PyTorch. So an array is like a contiguous segment of data stored in memory. That's just what an array is, if you did not know. But an array of PyTorch basically means that why would we not use a normal array? So it could be higher dimensions and it could be like different computation that is not super streamlined to vector algebra or matrix algebra that we want to use. So That's what it means by they're much more powerful than standard arrays or lists in Python. Okay, so next. So tensors have the same functionality as NumPy arrays. So NumPy, so NP arrays, if you've heard of them. If not, I feel like it should also be all right. And they can also perform auto differentiation, which will be great for our feed forward and back prop. So that's also why it's good. Okay, so how do we initialize a tensor? Okay, so let's just kind of look at this code. And this is using a Python list. So a Python list, if you've coded in C or C++, so you've probably seen an array. A list is basically an array, but it can be like you can add things as you go on. For example, in a C array or C++ array, unless it's dynamic, you can't really append things on there. But here you can as we go on. If you don't know about that, it's all good. So it's just basically a collection of items. So it can be like a collection of numbers, collection of whatever you want, collection of objects, let's say. So, okay. So as we can see here, we have two rows. So 5.2 and 2.3 would just be the first row, and 4.3 and 4 point, which is just 4, but with a significant digit, would just be 2 rows and 2 columns as expected. So if we just kind of look at this on a higher level, each bracketed region besides the outer brackets are 1 row. So that's yeah, that's what the code is doing here. So this creates a tensor object based on that. All right. Next up, we have initialization. So as you probably have seen, if you've created any collection of objects in any programming language, you might want to initialize it to have a certain type or a certain number of objects or a certain value for those objects when you're first creating it. Or you can just choose not to do that and like add on later. But if you do know, and I think tensors don't allow for reinitialization, but I don't necessarily know. You could check out the documentation for that. But the torch, the tensor for PyTorch, you can initialize using torch.once, which means fill it up with once, fill up your tensor with once. And torch.zeros means that fill the tensor up with zeros, and torch.rand is random number, so it fills up with the random numbers. So let's just kind of look at this code segment here. So z equals torch.zeros 5, 2, 3, right? So this is essentially like the 3D array, so 5 times 2 times 3. So let's look at how this is structured, because this might help you like kind of visualize things. So there's like 5 blocks. So that's our first 5. So 5 blocks. So 1, 2, 3, 4, 5. And then we have 2 rows in each block. So 2 rows in each block. And then we have 3 columns in each block. So that's just a higher level of how to visualize things. So yeah, like the bullet points are just kind of referring to that, but like that's a simpler way to look at it. All right, so torch tensors manipulating dimensions. All right, so it is important to be aware of your dimensions. So like I said, if you have a smaller number of dimensions, you can just kind of look at it and see, oh, it's just like divided into blocks. Those are rows and those are columns, but you might have something that is not so user-friendly to look at, I'm saying. So it's important that you keep track of those dimensions, because whenever we do computation on it, we don't want to get a dimension error. So what that basically means is we don't want to run into an error where, so for example, you've seen matrices. We have to have it so like, for example, like we have two matrices and we want to multiply a 4x3 and a 3x4, and they kind of have to line together. So we don't want problems like that arising. So one way to kind of manipulate dimensions is to do torch.reshape. So that allows you to create new dimensions for the tensor object. So let's kind of look at what's going on here first. So we have a equals torch.tensor 5, 3, 2, 7. So that's just two rows. So 5, 3, 2, 7, 5, 3 being in the first row and 2, 7 being in the second row. So that's how it's organized. And then we just print it out and we do b equals torch.reshape a comma 1 comma 4. So what that's essentially doing is we're taking the 5, 3, 2, 7 and we're making it one row and 4 columns, right? So one refers to how many rows are there. So that would just be one row, and then we have 4 columns. So a way to split up 5, 3, 2, 7 in separate rows would just be kind of like lengthening it out. And we just print the size again, just to make sure that we have the right size. And other than that, we have squeeze. So what does squeeze do? Squeeze removes any dimension of size 1 from a tensor structure using torch.squeeze. So this is just kind of art like abstract, but let's kind of look at what the example is doing here. So tensor 5327, we saw the size was torch.size 1, 4 when we printed it out. But let's say we don't want the 1, right? We want to squeeze it. So we can take out the 1 by doing torch.squeeze of b. So b is just our modified version of a, which was just like 1 row and 4 columns. So we can just shorten it out to just 4. So why would we do this? This is great if you have matrices and you want to do dot product operations. So maybe this might not make much sense right now, but as we're just kind of going through, and maybe not even here, but maybe through the guided project, it'll make more and more sense. But yeah, this is just an introduction to tensors. All right. Okay, so torch tensors, operations. So what use would tensors be if we can't really operate on them, right? So we need some, like, it's just kind of like a matrix, right? If we can't operate on a matrix, there's not much of a big use that it would serve. So same thing with tensors. So we have adding tensors would have an element-wise addition. So it's just kind of like a matrix. So let's see for an example. Okay, so the top one. So x equals torch.tensor 2, 7, 3, 4, 1, 5. So you have separate rows with 2, 7, 3, 4, and 1, 5 for each row. And then we have torch.tensor 3, 7, 4, 5, and 3, 2. And we add those together. So we get 5 and 14, because 2 plus 3 and 7 plus 7 on your first row, and so on. You get 7, 9, and 4 and 7. And this should preserve the dimension or the dimensions of the beginning two matrices, because two tensors. It's the same thing as a matrix. Sorry for like intermixing the terms, but same thing. So you have two matrices of the same dimensions. They result in the same dimension matrix after you add them together. So a 3x2 and a 3x2 gives you a tensor of 3x2. All right. So multiplying tensors results in element-wise multiplication, not dot product. So I don't know if we covered the Hadamard product, but it's just the element-wise multiplication of each element. So like, let's also go over an example of this. So this should not be confused with like a matrix type multiplication. So let's just see what this is. So the So variable x, so torch.tensor is 273415, like the previous example. So y as the same previous example. So 2 times 3 would be 6, 7 times 7 would be 49 for the first row, right? And similarly for the second row, it'd be 3 times 4, 12, 4 times 5, 20, and 3 and 10. So this should also preserve the size of the matrix tensor, because you're not really doing any matrix multiplication. It's just 2 elements. So you should have the same size of the tensor. All right, I feel like that was straightforward. So, okay, so this is kind of where matrix multiplication comes in. And this is called a matrix product. Hence, you see why I'm confusing the words together. But you should probably also see why they're so similar. So matrix products can be achieved using torch.matmul, so matrix multiplication. So we realize that if we have 2 3x2 tensors, we can't really multiply them together, right? So a 3x2 and a 3x2 can't, the dimensions just don't match. So we got to have another variable y that really agrees with us. So 2, 7, 3, 4, and 1, 5 would be size 3x2, right? 3 rows, 2 columns. And y would be 2, 7, 2, 3, 1, and 1, 5, 2, 9, 0. So that would just be 2 rows and then 5 columns. So 3x2 and a 2x5 would be a 3x5 matrix or tensor, yeah. So here, it's just the same thing as you would do for a matrix multiplication. It's the same thing that you should probably expect. So that's what torch.matmul is. Okay, so next, the autograd. So tensor can have operations recorded for auto differentiation. So remember how we said that there was something that was very special about tensors that wasn't really in or as an innate feature of Python lists. So that's kind of the autograd thing. So the auto differentiation feature, which makes the backpropagation algorithm very easy to implement with PyTorch. So we have torch.tensor 1, -1, 1, 1 again, and then that's just 2 rows, and then requires underscore grad equals true. So this requires underscore grad equals true, turns on this auto differentiation feature, and we have out equals x dot pow of 2 dot sum, and then out dot backward, and then x dot grad. So what this is supposed to do is it's supposed to do backward propagation. But as a small exercise, I'd like you to kind of run through this and see what each part does. So what does this x dot pow of 2 dot sum do based on what we learned so far? Like by running the code, you could run the code and then you could do this. So like try spending maybe like 2 minutes kind of tinkering with the code and see what you arrive at. So you can like probably put your results in the chat and see. They're not too surprising, but it adds to interactivity. So if you're just wondering like where to put this, you can add another cell and you can just kind of run through this and then just delete it afterwards if you don't really want to keep it. Okay, all right. So out would just output 4 because it sums every element squared. Okay, yeah, that's right. And out dot backward, you probably guessed it, is just backprop. And then x dot grad is also that. So it would just give you the result of that after you do backprop. So that's what it's doing. So we can move on. Okay. So loading data. So we don't a lot with models in workshops, in this workshop especially, but data is the primary motivating force behind all machine learning, and we need data to learn from. So how are we going to do this? That's what we're going to concentrate on right now. Okay, so now Nikhil is going to take over in loading data and seeing how it relates to what we're doing on a higher level. So Nikhil, to you.
All right. Thanks, Preetham. So just a quick check-in. How's everyone following along with the code? Everyone able to, I guess, make their own changes to the skeleton code and follow along as we're getting these results? Has that been working well for everyone? Give me like a thumbs up if that's been working. If it hasn't been working, let us know too. Okay. Terry Pratik, I hope you guys are doing good too. I don't think it's maybe I missed it, but let me know if you have any problems. But with that, we will keep on going on to the next step, which is data loading. So far we've been looking through like exactly what Torch is. So we know Torch is our machine learning library for everything like neural network related. And so now that we have our basis set for like tensors and their usage, we can move on to exactly how to use these tensors to hold our data structures in a data set. And so our end goal here is to hold our MNIST data set. So remember that MNIST is a data set that exists, and it's really popular for having handwritten digits and giving you like a label on like what that digit is. And so we're going to create a class called custom data set to help us facilitate that process of having data points as well as labels. So in PyTorch in general, I guess through through Torch Vision as well as through these libraries called the library of torch.utils.dataset. A lot of data sets from that library section have like a very similar format of data sets. And so there's map style data sets and iterable style data sets. And so today we're going to have our own data set being modeled after a map style data set. And so to do so, we're going to create our own custom data set, as you see down here. And we're going to have it inherit two important built-in functions, I guess, or it's not inherit, but we have to have it override two important built-in functions called getItem and len. The underscores means that they're, I guess, built in to like the class and are pretty important. Also the constructor as well, which is init. And so the main things here are, even if you're not familiar with classes, no worries, we'll go through it right now. But we have a class called custom dataset. And we're going to have this thing right here called torch.utils.dataset. Does anyone have any guesses on what this section in parentheses might be? Like, why do we have this class in parentheses in our big class? Any thoughts on that?
Are you inheriting from that?
Yeah, exactly. Nice. That was a great guess. And so basically, like Jeffrey said, torch.utils.dataset is going to be our subclass. And so we're going to be inheriting most of the methods from that and then overriding a couple of methods to make it fit our use case. So that was a great answer. So basically, we're gonna have this function, this class dataset, do most of the hard work for us because we don't want to be redoing work that other people have done for us already. So now that we have that, we're gonna have a constructor. Is everyone familiar with what a constructor is? Or anyone need it? Or actually, better question is, anyone not know what a constructor is and want me to go over it? Okay, take that as everyone's good on this, but we are gonna have our constructor be defining the init function right here. So we're defining it and initializing two variables in our class, statements and truth, based on these inputs to our data set or to our class. And so basically we're gonna have our custom data set take in statements or basically like our data points and the truth or our labels, and we're gonna save them to our data set. So we're taking in like the actual data and the actual labels, and we're putting them in our data set. That's our initialization. Next, for the get item. So get item is useful for us when we want to basically, or when we want to get one pair of data point and label from our whole data set. And so, as you'd expect, this function from data set usually takes in a self and index, and we're going to have it do the same, but instead we're going to return both the statements. So we're returning the actual data point of index. So basically, if we have like 100 data points, we're going to return like the index number data point and the index, the corresponding label. So for a given index into our data set, we're going to return the data point and the label. And then lastly, for length, if you ever want to know how big your data set is, we're going to take the size, or we're going to take the length of our labels as the size of our data set. Any questions on custom data set? Because we're going to be building on this for the next couple of slides. All right, cool. Let us move on. All right, so now that we define how our custom dataset object or class works, we now need to instantiate one of those objects. And that's, we can play around with it a little bit to figure out how it works in general. So here we have a data set, or like we're creating a data set of 2 data points. So we have the inputs, which are sentences. And so one sentence is bananas are usually a good source of potassium. And the other sentence is apples are usually orange. And then our labels are going to be whether or not the statements are true or false. And so obviously we know that bananas are a good source of potassium because of research. And or apples are not usually oranges, or are not usually orange because that'd be really weird. So that's false. So now we have our inputs, our 2 inputs and our two labels. So now we can create a data set based on that. And so remember, going back to our class, our constructor from last slide, we take in the inputs as well, or like we take in like the data points as well as the labels. And so again, we're going to create a data set called fruit data set by taking in the inputs and the labels. And so now we have our data set. Then we can use our functions like get item and len to figure out or to test their functionality. And so fruit data set like get item 0, we'll get the first element in our, or get the first pair in our data set. So the bananas one. And then length will give us 2 because there's 2 inputs, or we have 2 data points in general, 2 labels. Cool. So now that we have this, we can use it in combination with Torch functions to load in our data set for like actual usage in our model. And so PyTorch has, I guess, like a sub library called torch.utils.data we've been working with. And one of the things that they have in that is called data loader. And so data loader, given a torch.utils.data.dataset, offers us a lot of really useful functionality to, I guess, work with our data in a really flexible way. And so we have things like lazily loading the data set. So basically, by doing this, if we have a really big data set, PyTorch will only load the parts that we need right now and not store the whole thing in memory. So that might seem quite, I guess, like unnecessary right now. But imagine if we have like a 10 million image data set and each image is like, I don't know, a couple megabytes. If you have 10 million of those images, that's a lot of storage you're saving for or using for that data set. And so what PyTorch can do is that instead of storing the entire data set in memory, we can lazily load it in so that we don't need to store the entire overhead at the same time. It's a nice feature to know about. It's not super important for like, I guess right now, but it's a good thing to know about in general. Additionally, we talked a lot about batches in the past. So batches are really useful for training our models. And so this data loader class can organize our data set into batches automatically so that we can just take the batches and feed it to our model. So really convenient right there. And then another thing we can do is shuffle the data automatically. So we see here that we have a shuffle equals true tag or flag. And so that will shuffle the data around so that it's like more randomness. And so we don't get problems with like certain data being used consistently at the same time. And so we get more variation in how we're learning. And so we don't get the same batches over and over and over again. So now we have an idea of what data loader does. Let's look at this code. And so we're going to have two data loaders, basically the same. We're just going to have different batch sizes just to test the difference in batch size. And so we can see here that enumerate, the function enumerate, it works in normal Python as well. It's a built-in function. It works with data loaders as well. And so what we can do is we can use an enumerate to figure out indexes as well as data points from our data loader. So we can go for index comma data in enumerate data loader 1, print the index and print the data. So as you see here, remember that our batch size is 1. So we're only going to have 1 data point per batch. And so since we're working in terms of batches here, we're going to have basically, as you see right below, the first print statement is going to be index 0. We only have 1 data point per batch, and we only have 1 label as well, because label and data point are linked together. Then similarly, the next print statement happens, I equals 1 now, and data equals this section. And so you can see that, in fact, the batch size is 1 because only 1 data point per index. Similarly, the second print statement right here works with batch size equals 2. And so we can see here, there's only 1 index of 0, but both of the data points are in this because of the fact that batch size equals 2. So we're going to be training on 2 data points together. So we're bunching them together. And so thanks to data loader, we can do this all really automatically, as well as like with no effort on our end. So really helpful. So that's just general loading data. So we have made a custom data set to play with our own data and use data loader to work with that as well. So now we're going to move on to our target data set called MNIST. So remember that MNIST I said before is going to be our data set of images of handwritten digits and the corresponding actual number that they are. And so we're going to use Torch Vision for that. And so Torch Vision is another like library within another library from the people who made Torch. It's basically a part of Torch. And so this library has a lot of really unique or really cool data sets for vision or computer vision tasks. And so basically anything with images and stuff, Torch Vision might have a data set for that. And so what we can do is basically use that data set for our training purposes. And so we see here that we had training data set equals torch vision.dataset.mnist. So we're getting mnist from here. And there's some fields here. The exact syntax is on the, I guess, of course, in the documentation. The important things to note are that we are using train equals true on this section to get training data. And we're turning them into tensors right here with transform equals 10 to tensor. And so notice that in the test data set, we don't have train equals true, but everything else is the same. And so now we have training data set and our testing data set. Anyone want to remind me why we have separate data sets for training and testing? Prevent overfitting. Yeah, that's one reason. Yeah. So like Jeffrey said, if we have a testing data set, we can check if our model is being overfitted, because if our test accuracy is way worse than our training accuracy, that means we've trained too hard on our, or we trained too much or too diligently on our training data. And so we're not going to be able to generalize over a lot of data. So in general, the test data set is being used to check like the general, like the real world applicability of our model, because it's never seen this data before while learning. And so that's the important part. So yeah, great job. And then we're going to use our trusty data loaders here for training data and testing data. And so we're going to pass in the data sets as well as a batch size of 16 and shuffle equals true. So same thing, we have a batch size and a shuffle equals true. We want to shuffle to make have like random batches every time. And we want to have a batch size of 16 just to make it not too big, but not too small. So remember that if we have a data set, a batch size is too small, we're going to have a lot of volatility in our training. But if our batch size is too big, we're going to have really, really small increments in our performance. So we're trying to find a middle point, which we said the 16 is a pretty spot for this model. Okay, so now that we loaded the data, we might want to see what it looks like. And so there's a library called Matplotlib that we can use to visualize the data. And so remember at the very beginning, we did Matplotlib, or for imports that Pete discussed earlier, we did import matplotlib.pyplot as PLT. So whenever you see PLT, it's always Matplotlib unless they're trolling you. So PLT is Matplotlib. Basically everything plotting is Matplotlib and PLT. And so we can use Matplotlib in combination with our data loader object to look at what our images look like in a visual perspective. And so what we can do is create an iterator over our training loader. Yeah, Matplotlib the pyplot. Yeah, as I said, yeah, exactly. And so what we can do is basically, we can take our training data loader and create an iterator over it. And so an iterator, we haven't gotten into much detail about it, but the important part about an iterator is that you apply to any iterable object. So like things like lists, arrays, ranges, that kind of object, things that you can like go over each element in a row, that kind of style object. And so what iterator allows you to do is basically call the next function. It's the most important part of an iterator that you can call the next function. And so this will give you the next, I guess, like mini object within like your iterator. So remember that in our training data loader, we have bunches of batches, so bunches of 16 images. And so if we call train iterator.next, we're going to get the first batch of samples or some batch of samples in our data set. And so this is going to be 16 images because our batch size is 16. What we can do is do that because our training data loader stores batches in terms of like inputs and labels. We can deconstruct that and make that individual. So what we're doing in line 3 is that we're splitting apart our batches into their like mini parts. So into the inputs and the labels. And so the inputs are like actual data and the labels are like what number it is. And so we have that. Then just to check out like what it looks like, we can like print out images, the input size and the label size. And so we see that here that the image size is 16. So batches are 16, and the images are 1 by 28 by 28. And then our labels are just 16. And so we have 16 basically total data points in our batch, right? So that's why we have 16 there. And then here's where Matplotlib comes in. And so we're going to call a function called matplotlib.pyplot or plt.imshow. Imshow is one of the most used functions for showing data, or like basically putting an image on a screen. And so when we call imshow, the first argument is going to be what we want to show. It's like what, I guess, array or vector we want to like put on a screen. And so we're going to take our first data point from our batch. We're going to squeeze it to like a long vector. And that's going to be our thing we're going to show on the screen. And so next input is called CMap or color map. And so that's just like a stylistic thing. But CMap, this basically means that we're going to have a gray color scheme of like black, white, and gray. And so as you can see on the right, we have a black background, and we can see the number 7 is it's a really bad 7, but someone wrote 7 like this. So 7's right here. And so we've drawn it. And then we printed also the labels of that thing. So we printed out that this is actually a 7. And so we can see that the image as well as the label. All right, I think, wait, is it? Yes, I will. Wait, sorry. No, it's still my part. My bad, guys. Slide numbers are confusing. All right, so now we're going to move on from data to model building. So we have our data, we have like tensor knowledge. Now we need to move on to like actually building the model. And so the way we're going to do that is building off a class called torch.nn or neural network, torch.nn.module. And so we're going to basically build off that class. And so as a result, every layer we define using that is also going to be a module. And so by having our model be like a module itself, our model is basically going to be made up of a bunch of sub-modules that will form a tree structure. It's a bit confusing wording, but basically what we're saying is that our model is going to be a module class, and each of the layers will also be somewhat like that. And so by doing so and making our model out of many different layers, we'll be having our model be a bunch of sub-modules. And so it'll be like that. It'll be more clear in the next slide. And so you can see down here that again, we're going to have a class called class risks. We're going to have a class called custom model. As I just talked about before, it's going to import or it's going to inherit from nn.module. And then we're going to have two important functions, the constructor and a forward function. So forward is basically our feed forward routine. So what we're going to basically, it's going to say what layers are we going to apply for our model in general. Well, initialization, this is like where we define a submodules, or like where we define like the layers we're going to use. Like, are we going to use like a convolutional layer? Are we going to use like a feed forward layer? We define the layers here in initialization, and then we actually like use layers in forward. And so forward takes in an input, and we propagate the input through our layers. We'll see that in a second. So now that we've seen the class outline, we can go into actually implementing more of our stuff for the model. So we see the forward function, right? The good thing about Torch is that Torch has a function called __call __. Basically, it's an important function that like whenever you use your custom model, you don't have to actually explicitly call the forward function. It will do that for you, as well as any other like hooks or functions that you include as well. And so this is basically why you never want to use forward, because you might have some other things that the module will want to do ahead of time before doing forward. So you basically never use forward as like this thing itself. You basically always say like custom model and then pass in a data set, pass in a data point. We'll see that in a second, but just to make it clear, we're not going to be calling forward. There's going to be like a function called call that runs in the backend that will do that for us. Now that we have that out of the way, let's go into our actual model. So we're going to take in an input dimension as an output dimension to make our model as flexible as possible. So we're going to have 3 linear layers. Of course, you could spice it up by adding other layers, but that adds a little bit of complexity. And so our goal today is to just get familiar with PyTorch and stuff. So we're not going to go into convolution layers today, but we'll go into them in the future. But the important thing here is that we're going to have 3 linear layers. The first one's going to go from the input dimension to size 256. Next one's going to go from 256 to 128. And the last one's going to go from 128 to output dimension. And so you can basically see that, like, as you go through the layers, the number of hidden nodes decreases. It's not always the case in every model, but it's just for our model in general. And then now we're going to use forward to apply those functions. So given an input X, we're going to run it through layer 1, call ReLU on it. ReLU, remember, is one of our really useful activation functions. We're going to do the same thing for layer 2, and layer 3 is we're going to just apply layer 3 by itself. And so now we have that model set up. And so a question I have for you all is that, with our current structure, okay, this is a bit of a hard question, but like, given the fact that we have our MNIST data set of like that had of 28 by 28 pictures, and that we want to predict one of the 10 classes of outputs from 0 to 9, what do you all think the input dimension and output dimension will be for our model, for the MNIST data set in particular? It's a bit of a hard question, so even thoughts are fine. 16 and 10 batches, so 784 and 10. Nice, nice. Yeah, I think Perry has it exactly. I think, Jeffrey, you're on the right track. So we want to output, both of you guys said we want to output a 10, which is correct, because we want to basically narrow down to 10 output cells that basically predict the probability of it being a certain number. And so we take the maximum of those 10 output cells and we figure out which one we want it to be. So that's 10. As for the input, so we have a 28 by 28 picture, right? And so we need to pass in the entirety of the picture into the model. And so what we're going to do basically is that we're going to squeeze our input to a one-dimensional, so that's 784, as Terry said, and then pass that into the model. And so remember that even though our batch size is 16, we're still passing in individual images into our model, but the size of 16 means that we're going to backpropagate every 16, I guess, data points we pass in. So yeah, it's a tough question, but you all did really well on that one, so great job. All right, any questions before I pass it on to Angeline? Because that was a big section. All right, cool. I'll pass it on to Angeline for training.
All right, perfect. So now that we have, built our model, now it just comes down to, training our model and getting it fine-tuned to where it's actually functional and able to make the predictions that we do want it to make. Right. So before we even really begin training, there are a couple of things that we have to do beforehand. More specifically, there are 4 things that we need to train our model. So first of all, we obviously need data, but luckily we have already defined that with our data loaders. And then the second thing that we need is that we need to be able to create an appropriately initialized custom model object. So if you guys look at the code at the bottom of the page, you can see that we have to create an instance of our model called myModel using the custom model. And then we are going to pass in 2 parameters. So because the model is not using like CNNs, but instead like linear or fully connected layers, we need to ensure that the things that we pass in are actually flattened and squeezed. So this is why the input is going to be 784, because if you remember, the original dimensions was 28 by 28. So when we flatten it, we will get a total of 784. And then our output, because we're classifying digits, there are 10 different digits, and therefore we want to have 10 different classes as our output. So that's basically just that one line of code. And then the third thing that we need to do is that we need to be able to understand exactly how well our model is doing, right? We can't just train and train and train without really knowing like what's going on and knowing like where we need to improve on. And so that's where the loss function will come in. And so if you look at the second line of code, we define our loss function using using cross entropy loss for the model. And I'm pretty sure like cross entropy loss is like the pretty like standard one to use for like gradient descent. And so essentially, like if you're ever kind of like stuck on this sort of like issue, it's always like a safe bet to go with like cross entropy loss, and then you just import it from the library. And then the final thing that we need before we train our model is essentially an optimizer. And so what an optimizer will do is that it will allow us to just essentially update our weights and biases in the network after we go through back propagation. So after we kind of figure out like what's wrong with our model and try to fine tune it, we just need a way to be able to apply the changes and improve our model, which is where our optimizer comes in. And a very popular optimizer is just Atom. And this is the one that we're just going to be using today. All right, so with training, yeah, it looks like a lot, but don't worry, we're just going to help you guys break it down into pretty easy steps. So essentially the first line of code at the bottom of the screen, when it says for epoch in range 10, it is essentially just saying for every epoch, and we have 10 epochs. So it's just going to go through every epoch one by one. And then within our epochs, we have to evaluate each batch by itself. So essentially we have like our epoch for loop, and then within that for loop, we're going to go through each of the batches that are inside of the epoch. So then the first thing that we do with each of the batches is that we just need to unpack the tuple that we have into the inputs and the labels using like our data from the training data loader. And then from there, we also have to make sure that we do any necessary reshaping of our inputs, because remember that we are working with linear layers and fully connected layers. So it is important that we do reshape our data to be the appropriate, input, or else the model is not going to work really well. And so if you look at, I think it is the, it is the second line of code in the nested for loop. And so essentially what we want to have is that the first number that we have is 16, because there's going to be 16, I guess, elements inside of each one of our batches. And then for each of the for each of our like inputs, each of our 16 inputs, we need it to be a flattened tensor essentially. And so each one is going to be 784 pixels. So it will be like 16, I think, rows and then 784 columns. And so that is just the reshaped size that we need for our batch inputs for the linear layers. And then the next step, this is really important. So before we really do anything, like before we feed forward or like compute the loss and like back propagate, we need to make sure that we clear the gradient buffer. So essentially, every single time we like go through these for loops, the buffer doesn't necessarily clear itself. And so what will happen is if we don't clear it, it will continue to accumulate, right? And then so for every single, I guess like every time we do back propagation and every time we like update our like weights and biases, we don't really want the accumulation there. We want to start off with something like fresh and new. So that's why we always have to make sure we clear the gradient buffer before we really do anything. And then so after we do that, we just feed forward all of our data into our model. And that would be the line that says predictions equals my model. And you just feed in the batch inputs, which is your data. And then after you feed forward and the data all runs through the model, now you just have to check and see like how well did your model do. And so this is where we compute our loss. And so as you can see, the way that we compute our loss is using the loss function that we had previously defined before in the previous slide. And this will essentially just tell us how well our model is doing, and it will help us understand how we can improve when we do like backpropagation, which is the next steps. So after we figure out the loss, we just backpropagate, we just readjust our weights and our biases. And then after we backpropagate, now we just have to take whatever changes that need to be implemented, and we just have to implement those changes using the optimizer.step. And the final line is just a line that you guys could use if you want to like print things out just to see how like your model is doing after each epoch. Yeah, so that's like essentially training. And so after we've trained our model, now the important thing that we have to do is we also have to test our model, right? To make sure that there's no like funny business going on, and just to see how well our model is able to do on completely like new data. And so if you guys look at the line of code, essentially it's pretty similar to our training model. However, this time we don't really need to compute any of the gradients when we're testing the model's accuracy. And then so once again, for all of our data, we just have to break apart the tuples, and then we have to make sure we reshape our data, and then we feed forward all of our data into our model. And so this is just going to test to see how well our model is able to, you know, make predictions on like completely brand new data. And then from there afterwards, we just have to figure out like how accurate our model is. So the total is just going to be like just the total like number of like things that we pass through. And then with correct, we just have to be able to find the sum of the number of items we were able to correctly classify, which is what we use like the dot sum and dot item for. And then after we like test our model through all of the data, we then can just figure out our accuracy by just printing it with that like one line at the very bottom. And then, yeah, so essentially when we like ran it, the accuracy was like 97, like about 97%, which is like pretty good. So that's essentially what testing is. And then just a couple of like miscellaneous topics that might be useful for you guys. We have visualization again. And so I know that like Nikhil and like Preetham like probably already like covered this, but we are able to once again use like visualization with Matplotlib just to kind of like understand how the model is doing like throughout the training process. And then so basically just the first two lines of code is just you essentially like getting all of the samples, and then just remember that when you do like plot IM show, that is to set up the visualization for like when you are training. And then from there, you just once again reshape all of your data, and then you pass it through the model, and then you just print their predictions, and then you essentially print the label of like what it was supposed to be. So you can kind of see for like every single input, you're able to see like, oh, did the model like correctly predict it? And as you can see in the example, the model predicted that it was 4, the label is 4, and the image is 4. So it's like just a nice way for you just to verify that like things are going well in your model. So this is just like one tool that could help when you guys like are doing like a guided project or something. All right, and then the final, I guess, like tool or topic we're going to cover is just like saving and loading your data. So, I mean, just as kind of like the name implies, saving the data or like saving the model is just us saving like the weights and biases that you guys got when you trained. because it would just be very unfortunate if you like trained and you tested and you found these like really great weights and biases that like worked amazing, but then you didn't save it, and so you would just have to keep starting over from scratch. And so that's really inefficient. So to kind of aid with that, there's this one line that we can use, which is where we are able to store all of your weights and biases using torch.save. And then this will essentially access the model and store everything in like a state dictionary. And yeah, so essentially this is what like this line is for. And then, so like once you save your data, and then let's say that like one day you want to like access that model with those weights, so like the trained model, this is where the loading will come in. And so the loading lines will help you essentially take whatever you saved and then just load it into whatever model you need it to be loaded on. All right, and so we weren't able to like cover everything that you guys like, well, we weren't able to cover everything in like super fine detail. So there's always documentation just in case you guys like find yourself working on the project and then maybe have like a question or two about like parameters or like how you should be like approaching the architecture. And so this is what we have here is like PyTorch's documentation. It's extremely detailed and it gives you like a lot of good suggestions. And so like whenever you might be feeling like a little bit lost or unsure of like how exactly to use a function or like what libraries you should be using, you can always refer back to like PyTorch, or you can always ask us. So we're just giving you as many resources as possible for both like the guided project and if you guys do projects in the future. All right, so that was our rundown of PyTorch today. And so if you guys have any like questions for the three of us, just feel free to ask. Or if you need like any help with like setting anything up like later, we'll always be here for like questions and stuff. All right, if not, thank you guys so much for coming. Don't forget to fill out the anonymous feedback form if you guys have a chance. And then we also have a link to the solutions for the code that we were running today. So just to give you guys like a reference on how everything should work. And yeah, thank you guys so much for coming. We'll be starting our guided project next week, which should give you guys kind of like a taste for how projects would be like, and to like kind of give you guys an opportunity to see if like this is something that you would like to pursue. Yeah, if not, if you guys don't have any questions, thank you so much for coming again and have a great rest of your day.